Welcome to month 5 of the DevOps engineer track. In months 1 through 4, you built a CI pipeline, containerized the BISTEC Mart application, deployed it to Kubernetes, and provisioned that cluster with OpenTofu. You now have a running platform. But here is the question. If something breaks tonight, how would you know? How long would it take you to find out? Would the first alert come from a monitoring system or from a user? That is exactly what this month addresses. Observability is the ability to understand the internal state of a system from its external outputs, the metrics it emits, the logs it writes, and the alerts that fire. By the end of this session, an engineer responding to an incident will be able to answer, "Is this service healthy?" in 5 seconds, and "Why isn't it?" in 5 minutes. The 5 learning objectives are: instrument a service with Prometheus metrics, write PromQL for the 4 golden signals, build a Grafana dashboard that answers service health in 5 seconds, author Alertmanager rules with multi-window burn rate thresholds, and link every paging alert to a published runbook. Observability has 3 pillars: metrics, logs, and traces. Each captures a different kind of signal, and each has different cost and value characteristics. Metrics are cheap, aggregable time series numbers. They are cheap to store, fast to query, and excellent for alerting and dashboards. A metric like HTTP requests total tells you the rate of requests to a service, but it does not tell you which specific request failed or why. Logs are rich event records. Each log line is a structured or plaintext event with full context, the exact request parameters, the stack trace, the database query that timed out. The problem is scale. At high traffic, services emit thousands of log lines per second. Loki addresses this by indexing only labels like namespace and pod name, not the log content itself. Full-text search happens at query time over compressed chunks. Traces connect one user request across every service it touched. When your catalog service is slow, because a database call inside it is slow, traces show you the exact span where time was spent. Distributed tracing via Tempo and OpenTelemetry is previewed this month and explored in depth in the Senior DevOps track. Now, the most important concept in this slide: cardinality. In Prometheus, every unique combination of label values creates a separate time series. If you put a user ID in a metric label, you get 1 time series per user. A system with 100,000 users produces 100,000 series for a single metric. Prometheus will run out of memory. Good labels have bounded cardinality, status codes, HTTP methods, route templates. Never use raw URLs, request IDs, or user identifiers as metric labels. Prometheus has 4 metric types, and picking the wrong one is a common instrumentation bug. A counter only goes up. When the process restarts, it resets to 0. But the rate function handles that correctly. Use counters for requests, errors, and bytes processed. Anything you want to track the rate of. Never query a counter's raw value in a dashboard. Always wrap it with rate, or increase. A gauge can go up or down. It represents the current value of something: in-flight requests, queue depth, memory usage. Query gauges directly, or use delta, to observe change over time. A histogram samples observations into predefined buckets and counts them. Use histograms for values with a distribution: request duration, response size. From a histogram you compute P50, P995, and P99 latency using histogram quantile. The bucket boundaries are defined when you instrument the code. The critical advantage: histograms can be aggregated across multiple replicas, which makes them the right choice in Kubernetes, where every service has multiple pods. A summary is similar to a histogram, but computes quantiles client-side, inside the application. Summaries are more accurate for a single instance, but cannot be aggregated across replicas. In distributed systems, Prefer histograms. The decision guide. If the value resets on restart, use a counter. If it represents a current level, use a gauge. If it has a distribution you want to slice into percentiles, use a histogram. The 4 golden signals come from Google's Site Reliability Engineering book. They represent the minimum set of signals required to understand whether a service is healthy. Latency measures how long requests take. Track P50, P95, and P99, not the average. The average is deceptive. If 99 requests complete in 1 millisecond and one takes 10 seconds, the average looks fine while one user has a terrible experience. Also distinguish latency for successful requests from latency for failed ones. A 500 that returns quickly looks fast, but is not healthy. Traffic measures demand on the system. Requests per second broken down by status class. Traffic gives you the denominator for error rate calculations and the baseline for capacity planning. Errors measure the rate of failed requests. 5x responses as a fraction of total traffic. The SLO defined later in this session is based on this signal. A 1% error rate sustained for 5 minutes is a paging condition. Saturation measures how full the service is. CPU throttle, memory pressure, queue depth. Saturation is a leading indicator. It degrades before errors spike. Monitoring errors alone is reactive. Saturation gives you the chance to respond before users notice. The USE method on the right applies the same thinking to infrastructure resources. Utilization measures how busy the resource is. Saturation measures how much work is queued, and errors counts error events on the resource. 4 golden signals for services. USE for infrastructure. Prometheus Stack installs the Prometheus operator, which introduces a custom resource called Service Monitor. Instead of editing Prometheus scrape configuration directly, you create Service Monitor objects that tell the operator which services to scrape. The discovery flow works like this. Your application exposes a metrics endpoint. You create a Kubernetes service in front of it. You create a service monitor that selects that service using label selectors. The operator watches all service monitors in the cluster and automatically synthesizes the Prometheus scrape configuration. You never edit Prometheus IML by hand. Prometheus uses a pull model. It scrapes targets on a configured interval. Targets announce their availability by existing. No push is required. If a target goes down, Prometheus knows immediately because the up metric drops to 0. The most common configuration mistake is the release label. Prometheus Stacks Prometheus only watches service monitors that carry the label release. Prometheus Stack. If that label is missing from your service monitor, Prometheus silently ignores it. No error, no warning, no data. The diagnostic command is kubectl get service monitor and BISTEC Mart o YAML and check the labels section. The service monitor skeleton at the bottom of this slide shows the required structure. A selector that matches the service labels, and an endpoint definition specifying the port name, and scrape interval. PromQL is Prometheus's query language. Most day-to-day queries are built from 4 core functions: rate, MFIM. Takes a counter metric and returns the per-second average rate of increase over the past 5 minutes. Always use rate with counters. Never query a counter's raw value. It only goes up and means nothing without a rate window. Sum, by label, aggregates multiple time series into one, keeping the specified label dimension. For example, summing request counts across all pods in a service, while keeping the status class label. Histogram quantile, Q buckets, computes a quantile from histogram bucket metrics. The 0.95 value means the 95th percentile. The second argument is a rate and summed bucket metric that includes the label. Label selectors in curly braces filter which series you work with. Job catalog selects only the catalog service. Status file 5 uses a regular expression to match all 5x status codes. The 4 example queries shown here are the golden signal queries. Traffic as requests per second grouped by status class. Error rate as 5x divided by total, latency P95 using histogram quantile, and CPU saturation using throttled seconds. These 4 expressions are the foundation of the dashboards built in the next section. The first hands-on section adds Prometheus metrics to the catalog service. There are 4 steps. First, add the Prometheus client library to the catalog service, or Prom client if you are using Node.js. Second, add a metrics middleware that tracks HTTP requests total with method, status, and route labels, HTTP request duration seconds as a histogram, and in-flight requests as a gauge. Third, create a service monitor custom resource to tell Prometheus operator to scrape the catalog service. Fourth, verify the scrape is working by querying up job catalog at 1 in the Prometheus UI. The most important detail in step 2 is the route label. The label value must be a route template like cataloged, not the raw URL catalog 12345. Template routes have bounded cardinality. A typical service has a handful of routes. Raw URLs have 1 entry per unique URL ever requested, which grows without bound. The Python example on this slide shows the correct pattern. Define counter, histogram, and gauge metrics as module-level globals, then observe them in the request handler middleware, using the route template from the framework's router scope, rather than the raw request URL. Once metrics are flowing into Prometheus, Grafana visualizes them. A Grafana dashboard is a collection of panels. Each panel answers one question and visualizes the answer as a chart, stat widget, or table. 4 concepts govern how dashboards work. Panels are the individual charts. 1 question, 1 panel. If you need to answer 2 questions, use 2 panels. Variables are template placeholders like namespace and pod that inject into every panel query, making dashboards reusable across services. Time range and refresh control the default observation window. Last 1 hour with 30-second refresh is appropriate for most service dashboards. Do not set refresh below 15 seconds, as it adds Prometheus query load without meaningful benefit. Provisioning is the most important concept for production use. Dashboards must be exported as JSON, committed to Git, and mounted into Grafana via config map with the label Grafana dashboard. 1. Grafana auto-discovers these config maps. Never rely on dashboards that exist only in Grafana's internal database. They are lost when the pod restarts. The 3x2 layout shown here is the required structure for the catalog overview dashboard. Traffic and error rate on the top row. Latency percentiles and saturation on the middle row. Database query latency and catch hit ratio on the bottom row. Dashboard variables make a single dashboard reusable across different namespaces, pods, methods, and routes. Without variables, you would need a separate dashboard for every service. With variables, one dashboard covers the entire platform. The 4 required variables are namespace, pod, method, and route. Each is a query type variable. Grafana runs a PrometheusRule query to populate the dropdown with all current values. Namespace queries all active namespaces. Pod queries all pods filtered by the selected namespace. Variables chain together. When you select a namespace, the pod dropdown updates to show only pods in that namespace. When you select a pod, all panels update to show metrics for that pod. Multi-select allows selecting all pods simultaneously for an aggregated view. The 3 example panel queries on the slide show the variable injection syntax. Namespace, pod, method, where the variable names resolve to the drop-down selected values at render time. The acceptance criterion for the dashboard's deliverable is this. Selecting all namespaces should give a platform overview. Selecting a specific namespace should drill down to that service's metrics. The platform overview must answer, "Is everything healthy?" in under 5 seconds. Loki is a log aggregation system designed for cost efficiency. Unlike Elasticsearch, Loki indexes only labels, namespace, pod name, app name, not the log content. Full text search runs at query time by scanning through compressed log chunks. This keeps storage costs an order of magnitude lower. Prometheus runs as a daemon set on every Kubernetes node. It tails var log pods, attaches Kubernetes metadata as labels, and pushes log streams to Loki. The log lag target is P95 under 30 seconds. Logs should appear in Grafana within half a minute of being written by the application. The 5 saved log.ql queries cover the most common operational questions. The error-only query filters to log lines with level error, or HTTP 5x responses. The slow requests query filters to lines where the parsed latency exceeds a threshold. The JSON parsed query uses logql's JSON parser to extract structured fields from JSON log lines. The metric from log query uses rate over a log filter to derive a metric for a Grafana panel. The 5th query uses regex pattern matching to find specific error messages. LogQL syntax follows a similar structure to PrometheusRule. Start with a log stream selector in curly braces. For example, namespace BISTEC Mart, app, catalog. Then pipe through filter expressions. Saved queries in Grafana Explorer let any team member run these without knowing the syntax. In Prometheus stack, alert rules are defined as PrometheusRule custom resources, not directly in Prometheus DML. This keeps alerts in your GitOps workflow, committed, reviewed, and applied like any other Kubernetes manifest. The 5 required alerts cover the most common failure modes for the BISTEC Mart catalog service. Catalog pod crash looping detects restart loops before the service degrades completely. Catalog ifx rate fires when more than 1% of requests are returning 5x errors sustained for 5 minutes. Catalog latency P95 fires when the 95th percentile latency exceeds 500 milliseconds for 10 minutes. Postgres down fires when the database target drops from Prometheus' scrape pool, the most actionable alert, because the database is binary, either up or down. Cert expiring soon fires when a TLS certificate has fewer than 14 days remaining. The 4. Duration is critical. Without it, a single bad scrape fires the alert, and it immediately resolves. An alert that fires and resolves in 15 seconds is noise. The rule of thumb: 2 to 5 minutes for paging alerts, 10 to 30 minutes for warning severity alerts, and an hour or more for informational alerts. Every paging alert must have a runbook URL annotation pointing to a published runbook. This annotation appears in Alertmanager and in every notification sent to Slack or Discord. The runbook must be published before the alert is enabled. A 404 link is worse than no link. Service-level objectives turn the abstract goal, be reliable, into a measurable, actionable number. The chain works in 3 steps. The service-level indicator is the metric that measures what users actually experience. For BISTEC Mart's catalog service, the SLI is the ratio of successful requests to total requests, where success means the HTTP status code is not in the 5x range. Health check probes from Kubernetes and internal metrics scrapes are excluded. They would skew the denominator without representing real user traffic. The service-level objective is the target threshold for the SLI. 99.5% of requests must be successful over a 30-day rolling window. The error budget is what remains. 0.5% of requests are allowed to fail. Over a 30-day month, that is approximately 3.6 hours of complete failure, or a proportionally larger window of partial degraded service. The error budget policy translates the number into team behavior. When more than 50% of the monthly budget has burned, slow down non-essential changes. Prioritize stability over new features. When 100% of the budget is burned, freeze high-risk releases until the budget resets at the next window boundary. This is what makes SLOs organizationally useful. They create a shared, data-driven language between development and operations. The question is no longer, is the service reliable? It is, how much budget remains this month? A simple single-window error rate alert cannot distinguish between two very different situations. A brief 3-minute spike that barely dents the error budget, and a slow, sustained elevation that will exhaust the budget in a week. You would page on call for the spike and miss the slow burn entirely. Multi-window, multi-burn rate alerts solve this by checking multiple time horizons simultaneously. Each row in the burn rate table represents a different level of urgency. The fast burn alert fires when the error rate exceeds 14.4 times the baseline error rate for both the past 5 minutes and the past 1 hour. At that burn rate, the entire 30-day error budget would be exhausted in under 2 days. This is a genuine emergency. Page the on-call engineer immediately. The medium burn alert fires at 6 times the baseline over 30 minutes and 6 hours. At this rate, the budget is gone in under a week. Still a page, but with slightly more time to respond. The slow burn alert fires at 3 times the baseline over 2 hours and 1 day. The budget would be exhausted in under 2 weeks. This warrants a ticket, not a page. Important, but not a 2am emergency. The reason for requiring 2 windows simultaneously is flap prevention. A 5-minute spike at 14.4 times the baseline could be a deploy that immediately self-resolved. Requiring both the short window and the long window to exceed the threshold means the elevated error rate must be sustained before the alert fires. The Prometheus expression for the fast burn alert on this slide uses, and to combine the 2 window checks. Both must evaluate true at the same instant. If either drops below the threshold, the alert resolves. A runbook is the first responder guide for a specific alert. When an alert fires at 2 in the morning, the on-call engineer may be tired, stressed, and unfamiliar with this part of the system. A good runbook removes every decision that can be made in advance. There are 7 required sections. Title and severity declare the alert name and whether it pages or tickets. Signal shows the exact metric expression that triggered it. No searching required. Likely causes lists 3 to 5 common reasons the alert fires, in roughly descending probability. First pass diagnostic provides a checklist, the dashboard link, the command to check recent deploys, and the kubectl commands to inspect pod status. Mitigations offers quick actions. Rollback is almost always safe and must be included, and slower follow-up steps. Escalation defines exactly when to stop trying to fix it alone. After 30 minutes unresolved, page the on-call lead. Related alerts lists alerts that commonly fire together, supporting Alertmanager inhibition configuration. The live drill flow on the right shows the catalog high fix rate drill path. Alert fires. Click the runbook URL in Alertmanager. Open the Grafana catalog dashboard to confirm the error rate panel is spiking. Check recent deploys with Helm history BISTEC Mart. Inspect pod restarts and roll back with Helm rollback if a recent deploy is the culprit. The non-negotiable rule. Publish the runbook before enabling the alert. A runbook URL that returns 404 is worse than no runbook at all. It erodes trust in the monitoring system at the moment it is needed most. 2 topics belong in a peer architecture review: cardinality hygiene and alert noise. On cardinality, 4 patterns reliably cause cardinality explosions. User ID in a metric label creates one-time series per user. A system with 10,000 users creates 10,000 series for a single metric. Raw URL paths as labels create one series per unique URL ever seen, growing without bound. Per request IDs or trace IDs as labels have the same problem. The fix for all three is templating. Use root templates like users, status codes like 200 and 404, and HTTP methods like GET and POST. All have fewer than 100 possible values. On alert noise, 3 patterns make alert fatigue worse. Missing 4 durations cause flapping. A single bad scrape fires the alert and immediately resolves, training engineers to ignore it. Duplicate cascading alerts fire when a root cause like Postgres down triggers both a database alert and a downstream service error alert simultaneously. Configure Alertmanager inhibition rules so that when Postgres down fires, dependent service alerts are suppressed. The third pattern is alerting on metrics not tied to user experience. CPU at 70% may be normal. 5x rate above 1% definitely is not. The discussion prompt is worth spending time on. If you could have only one dashboard, what would it show? The answers reveal what each engineer considers most important for understanding service health. The best answers are business-aligned, revenue impact, checkout success rate, active users, not CPU graphs. The Month 5 challenge has 4 deliverables worth 25 points each, for a total of 100. Deliverable 1 is instrumentation. Add the 5 required metrics to the catalog and storefront services with correct metric types, templated root labels, and correctly bucketed histograms. Create Service Monitor custom resources for both services and verify Prometheus is scraping them with up A1. Deliverable 2 is dashboards. Build 5 Grafana dashboards, catalog, storefront, worker, platform overview, and SLO. Exported as JSON, committed to Git, and provisioned via Kubernetes config map. The platform overview must answer, is everything healthy? In under 5 seconds. Deliverable 3 is alerts and runbooks. Create 5 PrometheusRule custom resources with 4 durations and runbook URL annotations, and publish 1 runbook per paging alert before enabling it. Alerts without runbooks score 0 on the runbook subcriteria. Deliverable 4 is the SLO definition. 99.5% availability SLO for the catalog service. All 3 burn rate alert rows. 14.4 times, 6 times, and 3 times, with both windows each, and an error budget policy with named action thresholds. The passing score is 75 out of 100. An exceptional submission, 90 to 100, is one where an on-call engineer could survive a week using only what you built. SLOs and runbooks tied together, dashboards that answer real questions, and alerts that page only on conditions a human can actually resolve. You have covered the full observability stack. Metrics with Prometheus and PrometheusRule. Dashboards with Grafana and provisioned JSON. Log aggregation with Loki and PrometheusRule. SLO-driven alerting with burn rate thresholds. And runbooks that make those alerts actionable. More importantly, you have shifted from reactive to proactive. Instead of learning about an outage from a user complaint, you will know before users notice, and you will have a clear path from alert to diagnosis to resolution. Offline milestones extend what you built tonight. Adding tempo and OpenTelemetry completes the 3-pillar picture with distributed tracing. Provisioning dashboards via config map replaces any remaining UI-created dashboards and completes your GitOps coverage. Pira generates multi-window burn rate alert rules from a declarative SLO YAML, removing the need to handcraft the PrometheusRule. Wiring Alertmanager to Slack or Discord makes alerts reach the right people in real time. And the noise audit. pulling the last week of alert history and asking of every alert whether anyone acted on it, will change how you write alerts for the rest of your career. Month 6 is the CI/CD capstone. You will take the pipeline from month 1, the containers from month 2, the cluster from month 3, the infrastructure from month 4, and the observability stack from tonight, and wire them together into a complete, end-to-end delivery system. The SLOs you defined tonight will drive the release quality gates in that pipeline,